All right, this is going to be our lesson over linear approximations. That's going to be our main focus because that is an AP test topic that we will need to know how to do. Then we're also going to talk a little bit about differentials, just another way to do an approximation because it has some interesting properties and allows us to practice derivatives a little more. All right, so the tangent line is a useful way to approximate the value on a curve. All right, we write our tangent lines usually in point slope form. Which would look like this. That's from your Algebra 1 class. If we named our x1 value a, then we could write it in function form. F of a would be the y value, f prime of a would be the slope, and a would be the x1 value. All right, so when we're using a tangent line to find an approximation of a value on the curve, we might want to rearrange the terms on the tangent line to write it like this. So basically all they did was add the f of a over to the other side, and this y value is going to be your approximation. That's going to be the value that you want as your answer. All right, so y represents the y coordinate of a on the tangent line. This gives an approximation of f of a. So f of a is the real value of the function, and then the y in the tangent line equation is the approximate value. So the y coordinate of a on the function f of x is represented by f of a. F of a is the actual value. Okay, so here's our first equation. We have f of x is equal to x squared. So part A, we're going to write the equation of a tangent line at x equals 1. All right, so we know we need a point and a slope. All right, we currently have an x coordinate, so we need a y coordinate and we need a slope. So we can get the y coordinate by plugging our number into the function. So the y coordinate's 1. And then we can get the slope by finding the derivative and then plugging our number into the derivative. So our slope is 2. All right, so we get our tangent line equation of y minus 1 is equal to 2 times x minus 1. All right, part B. Use your answer to A to find an approximation for f of 1.01. Okay, so f of 1.01, our approximation for that is the y right here. So f of 1.01 is approximately equal to, so I'm going to add the 1 to the other side. 1 plus 2 times 1.01 is our x value, minus 1. All right, just work this out. That is equal to 1 plus 2 times 0.01. That's 0.02 plus 1, so it's 1.02. All right, part C. Find the actual value of 1.01. So now we're going to do f of 1.01, which is equal to 1.01 squared. All right, you can just plug that into a calculator. I don't have my calculator loaded up right now, so I'm just going to tell you what it is. It's 1.0201. So this is the actual value. All right, and then another thing that we like to do with approximations is figure out how far off we were. Right? If we're approximating something, we want our approximation to be a good approximation. So we want to be close to the real answer. All right, so you can find the error in your approximation, the amount of error. So we're not doing percent error, we're doing the amount of error, which is simply just a subtraction. All right, we put it in the absolute value. So the absolute value of our error would be equal to the absolute value, and then you subtract these. And since we're doing it inside an absolute value, it doesn't matter what order you do it in. All right, I usually try to put the bigger number first if I can recognize that, but it doesn't matter. You can put the 1.02 first. And so if I subtract these, the 1.02, those all turn into 0, so I end up with a 0.0001. And that's a very good approximation. And the reason it's so good is because we built our tangent line at x equals 1, and then we approximated at a number very, very close to 1.01. All right, if we had been asked to approximate like 3.72, then our approximation would not have been very good at all because our tangent line is not close to this number. All right, this number, you might want to build a tangent line at x equals 4, right? Because that would be the closest whole number that's close to the approximation. So, all right, let's try another one. Another way that you can use tangent line approximations is to approximate a radical. So we know a lot of perfect squares and perfect cubes and things like that, but it's helpful to be able to kind of have an idea of what a non-perfect radical would be. Okay, so we're going to do this for the cube root of 127. Okay, cube root of 127 is not a perfect cube, and we want to try to get an approximation for what this value is. Okay, so to do this, we're going to let f of x be the cube root of x. So that's our function we're going to be dealing with. And then we want to choose a perfect cube that is close to 127. Okay, we want it to be a perfect cube because we want to build our tangent line there, and we want to be able to know what the values are without a calculator. If we had a calculator, then we would just plug this in and do it. All right, so 125. All right, so we're going to let x is equal to 125. That's a perfect cube that's close to 127. All right, so we are going to start by writing a tangent line. So I need a point and a slope. So I currently have an x coordinate. I need a y coordinate, and I need a slope. So y coordinate I get by plugging 125 into my function. So the cube root of 125. That's equal to 5. All right, so I have my y coordinate. All right, slope, I need to find the derivative, f prime of x. So this is x to the 1/3, so I multiply by 1/3 x and then subtract 1 from the exponent, so negative 2/3. I'm going to put that negative exponent on the bottom, so 1 over 3 x to the 2/3. Okay, now I'm going to plug my number in, f prime of 125. So 1 over 3 times 125 to the 2/3 power. All right, so with a 2/3 exponent, I always start by doing a cube root first. Cube root of 125 is 5, and then I do 5 squared. So this ends up being 1 over 3 times 25, which is equal to 1 over 75. So that's our slope. And so now we can write our tangent line equation. Y minus 5 is equal to 1 over 75 times x minus 125. All right, so now we're going to use our tangent line to approximate the value of the cube root of 127. So the cube root of 127's approximation will be our y value right here. So the cube root of 127 is approximately equal to, we're going to add the 5 over, 5 plus 1 over 75 times, and then x value is 127. 127 minus 125. All right, well, that's equal to 5 plus, this is 2. So 2 over 75. And if you got 5 as a common denominator with 75, you would have, let's see, I need to multiply 5 by 75. So that's what, 350 plus 25. 375. Then plus 2 over 75. So that's equal to 377 over 75. All right, and that's our approximation. Okay, you could plug that into a calculator to get a decimal version of that. Plug in cube root of 127 to get that decimal version and see how close you are. I'm going to do that actually. So let me get my calculator loading up here. All right, so 377 decimal form over 75 is that. And then cube root of 127 decimal form is that. And then you can subtract those answers from each other and take the absolute value, and you get an error of 0.000141. All right, so pretty good. Again, very, very close. And the reason is because our tangent line built at 125 is very close to 127 on this one. So that's why we get an error that's so good. All right, and again, we didn't have to use a calculator. We got a pretty close answer, an answer that's within 1/10,000th of a point of our real answer. All right, on the back, we are going to talk about differentials. All right, so Leibniz used the notation dy over dx. We've been using that before. We call that Leibniz's notation to represent the derivative of y with respect to x. It looks like a quotient of real numbers, but really it's a limit of quotients because that's what derivatives are. They're limits in which the numerator and denominator go to zero, but don't actually equal zero. Okay, the denominator especially cannot equal zero because then we'd have something that's undefined. All right, so Leibniz actually did not really use the notation in that format. He separated them. He had dy and dx as separate entities, and he decided that they were called infinitesimals, non-zero numbers that are infinitesimally small. All right, so it's tricky to define these two things as separate entities, but we really only need to define dy and dx as formal variables. Textbooks usually just define them in terms of each other, so that their quotient must be the derivative. All right, so here's a definition that we're going to use. This comes from the Finney, Damano, Waits, and Kennedy calculus book. So we're going to let y equal f of x be a differentiable function. The differential dx is an independent variable. The differential dy is equal to f prime times dx. The variable dy is always a dependent variable, and it depends on both the variable x and the variable dx, or the differential dx. All right, so first example, we're just going to find dy. All right, and I like to just kind of do it as an algebra problem. All right, this may not be exactly perfect, but we end up using the same idea when we do differential equations later in the year. So I kind of like to introduce it here as well. Okay, so if we were doing this problem using Leibniz's notation, when we first learned how to do derivatives, I would have written my answer like this. The derivative of y is dy over dx is equal to the derivative of 5x cubed, which is 15x squared. All right, and that's it. We would just leave our answer like that. That's our answer. But today we want to get it in differential form. I want dy, so I want to get dy by itself. So I can get dy by itself by multiplying by dx. And I do that on both sides. And so I end up with dy on the left side is equal to 15x squared times dx. And that's what they're looking for in differential form. All right, so that's how you can think of it. You don't have to show this middle step. You can kind of just jump straight to here. And again, this is really just using this formula right here. dy is equal to f prime, which is 15x squared dx. All right, so we can use differentials to do approximations as well, just like we did with our tangent line. All right, so we have the radius of a circle increases from 10 meters to 10.1 meters. So they want us to use the differential dA to estimate the increase in the circle's area. All right, so we start out with the formula for area of a circle. A equals pi r squared. We're going to take the derivative in differential form. So dA is equal to, multiply by 2 pi r times dr. All right, we are trying to find dA. All right, so we're trying to find dA, and so we're going to plug in some values here. 2 and pi are constants. Our r is the original radius, so our original radius is 10, and then dr is how much the radius changed by. So it went from 10 to 10.1, so that's change of 0.1. All right, you can think of dr as like delta r. How much did r change by? All right, so that means that dA is equal to 10 and 0.1 actually cancel out. 0.1 is 1/10. 10 cancels, so dA is equal to 2 pi, and that would be in meters squared. Okay, so that's our approximation. We're approximating that the area of circle 2 is 2 pi square meters bigger than the area of circle 1. All right, so now we want to compare the estimate we found in part A to the true change, delta A. All right, so the true change is if we just plug both of these numbers into the area formula and subtract. Okay, so area is equal to pi times 10 squared. So that's equal to 100 pi. All right, I'll call this area 1. Area 2 is equal to pi times 10.1 squared. All right, if you actually notice, we've actually done this this square already. If we go back to this problem right here, when we did 1.01 squared, we got 1.0201, 4 decimal places, because we had 2 decimal places times another 2 decimal places. So you're going to get that same pattern, 10201. but this one's only going to have 2 decimal places because it's 1 decimal place times another 1 decimal place. So we get 1, 0, 2, 0, 1 with 2 decimal places, and then that's multiplied by pi. All right, and then our delta area is equal to area 1 minus area 2 in absolute value. Okay, so I'm going to actually put area 2 first, 102.01 pi minus 100 pi. And that's equal to 2.01 pi. All right, so our approximation was that our area changed by 2 pi, and our true change was 2.01 pi. Okay, so pretty close. Now we are multiplying by pi, so it's not quite as good of an approximation as our previous ones have been, but it's still pretty nice. All right, so we're going to find the error in our 2 approximations. So that's going to be the absolute value of 2.01 pi minus 2 pi. So that would be equal to 0.01 pi, which is equal to, and let's plug this into a calculator and see 0.01. I guess we kind of know what pi is, so we could just move that decimal place 2 places. So 0.031416. All right, so again, not as good as our other ones. Our other ones were like 0.0001. So this is 0.03, so a little further off, but still a pretty decent approximation. We're still within 3/100ths of the true change, which is pretty good. All right, now as you start to scale things up, your approximations get worse and worse. Okay, so now let's suppose we have the Earth, and we're going to pretend like the Earth is a perfect sphere. And we've determined its radius is 3,959 miles plus or minus 0.1 miles. What effect would that tolerance have on the surface area of the Earth? Okay, so you need the formula for surface area of a sphere. So this is it. S is equal to 4 pi r squared. And then we're going to take the derivative of that in our differential form. So ds is equal to, multiplied by 2, 8 pi r dr. All right, and then our change in surface area, ds, is equal to 8 pi, the original radius, 3,959, multiplied by the change in the radius. And you don't want to do plus or minus. Well, I guess you could do plus or minus. All right, let's put the plus or minus in there. So plus or minus 0.1. All right, now for this one, I'm just going to plug this right into the calculator and get a decimal value. All right, so 8 pi times 3,959 times 0.1. So 9,950.052. All right, that'll be in miles squared, square miles. All right, and just so we can do a comparison again, let's find our true change. So we'll do delta S. So S1 would be equal to 4 pi times 3,959 squared. 4 pi times 3,959 squared. So that 196,961,284. All right, move that over here for a second. Okay, so 196,961,284.337. All right, and then we're going to do S2, which would be 4 pi times, and you can either add or subtract 1. I'm going to add because it's easier, 3,959.1 squared. And again, this will be an approximately because we are rounding our answer. All right, so I'm just going to go copy this and put a 0.1 right there. All right, so 196,971,234,515. 196,971,234.515. All right, and then our delta S would be equal to the absolute value of S1 minus S2, which is equal to So we can just do a subtraction here, and I'll take that, and then I can do the absolute value myself if I need to. And there we go, 9,950.177910. So, I mean, again, we're going to be pretty good here, even at this large scale. So let's find our error. So our error is the difference in ds and delta s, again, in absolute value. All right, so I can take that number I just found, which is ds, and I can subtract from that the other value up here. There we go. And I get 0.125658. Okay, so again, it is a little bit worse even than our last one. It's off by 0.1 now, 0.125. 126, but that's still pretty good, pretty close. And this one was so much easier to find. We still had to use our calculator, but this one we had to plug this in and get that huge number, and this in and get that huge number, subtract those huge numbers before we got to our approximation. And this one we pretty much got right to the answer right away, and it was only off by 0.125. So differentials are pretty powerful for approximations. Again, not going to be covered on the AP exam. Differentials will not be, but your tangent line approximations will. So make sure you practice that on your worksheet, and I'll see you on the next video.